Now this is type 2, where we convert any other number system with base r to a decimal number system. Do you see? Now this is exactly reverse part of type 1. Type 1 we have seen decimal to any other number system having base r. This is exactly reverse. Now we are going to convert any other number system having base r to decimal number system. So let's say some number is given having base as r. I have to convert it into a number having base as 10. Let us start with this example. There is 38.25. Do you see the base is 9? Meaning that if I compare with the standard example I have given, meaning that r is equal to what? 9. Before you start solving this, what you have to do is you have to give their positions. Okay. What is meant by position? Do you see this is a decimal point? Before decimal point there is an integer part. After decimal point there is a decimal number. Meaning that mark this 8 with weight as 0, mark this 3 with weight as 1, mark this 2 with weight as -1, this with -2. Suppose we had one more digit over here, I could have written weight as 2, 3, 4 and so on. If I have more digits on this side, I can having weight as -1, -2, -3 and so on. What is the required base? Required base is 10. What is the given base? 9. What you need to do is you have to keep on multiplying every digit given over here with a given base. So as you can see, I'll write 3 into 9 plus 8 into 9. Where is a decimal point? Ignore. Write plus directly. 2 into 9 plus 5 into 9. Now do you see you have given some weights over here? You have to replace those weights as a power of those 9s. So 8 had 0. So I will write 9 to the power 0. 3 had a weight as 1, so I'll write 9 to the power 1. 2 had a weight as -1, now I'll write 9 to the power -1. And 5 had a weight as -2, I'll write it as -2. And if you actually solve this, you will get 35.28 to the base 10. So now we see a second example. It is given as AF.DB having base as 16. And you have to convert this into a number having base as 10. So what is the given base? It is 16. R is equal to 16. As we have done in the previous sum, you have seen each and every digit were multiplied with the given base. Same thing we are going to do. We have to multiply every digit with 16 now. But as I said in the earlier type, that whatever multiplications and divisions and additions or subtractions that we do are naturally in decimal. So you have to convert every given alphanumeric value into a numerical value. Alphabets into numerical value. Meaning A would be replaced with what? 10. F will be replaced with what? 50. What is meant by D? D comes after C, means that it is 13, and this is B is what? 11. So I have to multiply every digit with what value? Of course 16. So it is actually like this: 10 into 16 plus 15 into 16. 15 were representing F. What D were representing? It is 13. So it is 13 into 16 plus 11 into 16. If you remember what we did last time, we were having weights as 0, 1 before decimal point. After decimal point we have weight as -1, -2, etc. Similarly over here, before decimal point it is 0, 1. After decimal point it is -1, -2. You have to now treat them as a powers of 16. So with 15, I'll write it 0, here 1, -1 and -2. And if you actually solve this using your gate calculator, you'll get 175.85 having base as 10. So now this is what we called as type 2. So in type 2, it is very simple. Type 2, you have to convert any other number system to a decimal number system, any other number system with base r. Okay, take every digit, multiply with r, and according to their weights you have to write the power of the given base. Okay, this is how you actually convert any other number system to decimal. So now we will be moving to our type 3. Okay, as you can see on the board, type 3 says it is octal to binary and vice versa, hexadecimal to binary and the vice versa. So let's start with some example. 127 having base as 8, which is nothing but octal number system. You have to convert it into a number system having base as 2. So you actually convert octal to binary here. What you need to do is check every digit 1 2 7. Below every digit write binary weights as 4 to 1. Below every digit specify their binary weights as 4 to 1. If I have to represent this 1 into binary, do you find this 1 in this 4 to 1? Answer is yes. You find it over here. So below that you write 1, other bit are 0. Do you find this 2 in this 4 to 1? Answer is yes. I find it over here. So I have to write 1 over here and other bits are 0. If you actually look at 7, you see that 7 is not appearing over here. Then what you need to do is, you need to add them and see to it whether you get 7. For example, now 4 plus 2 is what? 6, and 6 plus 1 is 7. Meaning that to represent 7, below all digits you have to specify 1. Now whatever number have come, it is straight away binary number. So now this is 127 having base as 8 is straight away converted into a binary number. I am sure you are clear with this example. So this is first we have seen octal to binary. We will go vice versa. If I have to go from binary to octal, we will see binary to octal now. So in binary, let's say we have given combination as 101, let's say 1.11011 having base as 2. So now this is a binary number given to us. I have to convert this into number system having base as 8. Okay, if you remember, the octal number were given to you and you have converted into binary. What you did is, below every digit you written as 4 to 1 4 to 1 and you have written binary equivalent. Have you noticed something, that every digit gives you 3-bit binary? So it is vice versa. Now 3 binary bits will give you 1 digit of octal number. So you need to actually group it into 3 bits. Okay, for example, now this is an integer part. So integer part you have to group it in this direction, and after decimal point you group in this direction. The group should be of only 3 bits together, because you are knowing that the weights are 4 to 1. So what I'll do is, first group is what? 0 1 1. Above that I'll write 4 to 1. The other remaining one is over here. Even above that you have to write 4 to 1. But do you see 2 bits are missing? Obviously, to keep the values same, we are going to write them as zeros over here. So now where do you find 1? You find 1 only below 1, meaning that this is representing digit 1. Here where you find ones? You find ones below 2 as well as below 1. So you need to add them. 2 plus 1 is what? 3. So now this is 13 is the digit. Now this is a decimal, a number which is coming decimal point, before decimal point. When you are starting after decimal point, you start grouping in this direction. But don't forget that you are going to group it into 3 bits only. So what is the first group that you get is 110. As you can see, after decimal point 110, this becomes the first group. What is the second group? Second group, we are having only 2 ones. Do you see 1 bit is missing? Of course, to keep values the same, you write 0 over here. And again on top of this, you are writing the same binary weights, which are 4 to 1. Now where you find ones? You find ones below 4 and 2. Add them, you get 6. Again add them, you get 6. Finally, we have 13.66 having base as 8. This is the final answer. This is how we actually convert binary to octal. So now what we have to say is hexadecimal to binary and binary to hexadecimal, and then we will done with this type. So first is hexadecimal to binary. First example, let us take. I have taken some random number having base as 16. I have to convert it into a number system having base as 2, because I have to convert hexadecimal to binary. If you remember what we did in octal, okay, what we did in octal is below every digit we expressed every digit as 3-bit binary number. In hexadecimal we express every digit with 4-bit binary number, meaning that weights will not be only 4 to 1, weights will be now 8 4 to 1, meaning that A के below you have to write 8 4 to 1, below 2 you write 8 4 to 1, after that there is a decimal point, below 5 you will write 8 4 to 1, below B you will write 8 4 to 1. If you remember in earlier type, I told you whenever alphabets are coming you have to replace them with a decimal equivalent. So now there is A, so you replace A with 10, you replace B with obviously 11. So consider A as 10. So if I have to represent 10, I don't find 8 4 to 1 के अंदर 10. Okay, so what you need to do is you have to sum up some digits, and so as to you have to manage to get 10. So how do I get 10? I know that 8 plus 2 is 10. So below 8, below 12, write 1. Other bits are 0. 2. It is easy to get 2. You can look at 2 over here. So below 2 there is 1. Other bits are 0. After this there is a decimal point. You find 5? No. But you have to sum up some digits and manage to get 5. So I can see that 4 plus 1 is 5. So below 4, below 1 I'll write 1. Other bits are 0. Last, B. What you are representing B as 11. You don't find 11 over here, but you can sum up some digits and manage to get 11. So can I say 8 plus 2 plus 1 is 11. So below 2, below 8, below 2, below 1 I'll write 1s and other bits are 0. Finally, whatever number I have come, it is representation of hexadecimal to binary. Now we will see a reverse way, meaning that now binary will be given to you, have to convert it into hexadecimal. So now this is the type we are going to see. A last sum. 101.011. Let's say 10. Having base as 2, you have to convert this into hexadecimal now. If you remember, we did binary to octal before some time. If you remember binary to octal, I told you before decimal point you have to group from right to left. After decimal point you have to take grouping from left to right, and every time you were grouping only 3 bits. And if you remember, in hexadecimal we represent every digit with 4-bit number. So here you are going to do the same kind of grouping, but grouping will be of 4-bit numbers together. So before decimal point we will group in this direction, after decimal point we will group in this direction, but don't forget that we are going to group 4 bits together. So if I actually start grouping here, do you see I have a deficiency of 1 bit, so I write a 0 over there and point. After this, if I actually start grouping, I get 0, 1, 1, 1 in one group, and I get only 0 over here. Now to complete this 4 group, I have to write zeros over here, and top of this I write 8, 4, 2, 1 as binary weights. These are fixed binary weights. So where do I find 1? I find 1 below 4 and below 1. So 4 plus 1 is 5. So 5. After that there is a decimal point. After that, do you see 4 plus 2 plus 1, meaning that you get what? 7. Here everything is 0. I can write 5.70. In fact, you can write only 5.7 having this as 60. And this is how we actually convert from binary to hexadecimal. So now we have completed all the types, and I would now say the number system part is completed. In the next lecture we will actually see the problems based on this, and we will be actually seeing how gate problems are going to come on this topic. Thank you.